In this screencast, we're going to look at the chemistry of aldehydes and ketones. So aldehydes have the general formula RCHO. And remember that we're using R as any group, sort of like a variable in algebra, like X. So really we're looking at CHO. That is indicative of an aldehyde. And so if we draw that like a Lewis dot, the CHO is this part. So notice that this connectivity doesn't really match that as the abbreviation. But that's an aldehyde. And so what about a ketone? So this one I'm going to say R, say 1COR2. And the Lewis structure would be the following. So this is where we really have to pay attention to how these sort of line formulas are in transforming them into a Lewis structure. So here's our carbonyl. We have R1 and R2. Those both have to be carbon so that we actually have a ketone. So the difference between an aldehyde and a ketone is the aldehyde has the H directly bonded to the carbonyl. The ketone has two carbon groups. So let's go ahead and look at some nomenclature. And so one way that I found to be very positive when I was learning organic chemistry was to try to identify trends and really put those trends into a table. So what I want to do here is say carbon number in this column. Then I want to say aldehyde. Then I want to say ketone. So for one carbon count, that aldehyde would be called methanal. So we're taking one carbon methane, we drop the E, and we add Al. So that Al is indicative of aldehyde, so methanal. So we cannot have a one carbon count ketone. What about two? So if we have two carbons, so ethane, we put a carbonyl in. So this would be not ethane, we drop the last E and we add Al, so ethanal. So there we go, Al. So the aldehydes are all going to end in Al. We cannot have a two carbon count ketone. So we get up to 3, and now let's draw propane. So now we have a choice. Where is the carbonyl going? So for an aldehyde, it always has to be at the terminal. That's what an aldehyde is. So this would be propanal. So there's our Al. So we can actually have a ketone now. So we draw our 3 carbon count. Now the carbonyl has to be in the middle. And so it's a propane derivative. The carbonyl is here, so it's a ketone. So instead of, we're going to drop the E and add ONE of the name. So this is going to be propanone. So ONE. We drop the E of propane, we add ONE. So I'm going to probably take us up through carbon count 5 to illustrate something important here. So 4, 1, 2, 3, 4. the carbonyl must be at the terminal. So butane, we drop the E, we add Al, butanal. 1, 2, 3, 4. So this is a 4-carbon count. The carbonyl has to go in internal. So here, we're making the same thing. So let me just draw that again. I put it there. Those are both the same compound. So this is going to be butanone. So again, O-N-E, O-N-E. So as we've seen so far in Organic 1, now Organic 2, when you see this word butanone, you're seeing this parent functional group of this 4-carbon chain. So butane, B-U-T-A-N, 1, 2, 3, 4. One, that's the ketone. So this is what you should see in your mind's eye and be able to draw. Again, these are equivalent structures. So let's go up to 5, and we're going to see the actual difference now in the ketone. So 1, 2, 3, 4, 5. So pentanal, so Al, that tells us it's the aldehyde. So let's draw our 5 chain. So there's 5 carbons. Let me number them. 1, 2, 3, 4, 5. Now we see with a 5-carbon chain, we actually have the 2 and the 4 positions are equivalent, but the 3 is different. So we can actually have 2 different ketones for carbon count 5. Let's go ahead and draw the first one. So we actually now have to specify where the location of the carbonyl is. And so we're going to do that by saying 2 pentanone. So O-N-E specifies that it's a ketone. The 2 is telling you where that carbonyl group is. So the other constitutional isomer of this is going to be 3 pentanone. So again, that's telling us the 3 is telling us where the ketone is. So 1, 2, 3, 4, 5. And think about what we've done so far in Organic 1. How would you differentiate these 2 constitutional isomers? Say, for example, using unique number of carbons. This one would actually have 5 unique carbons. So 1, 2, 3, 4, 5. The 3 pentanone would have 3. So 1 and 5. 1 and 5 are the same. 2 and 4 are the same. 3 is its own thing. So 1, 2, 3. So by carbon NMR, we could differentiate these. So what about if obviously what's in common with these functional groups, aldehyde and ketone, is the carbonyl. So carbonyl is, if we recall from IR spectroscopy, what I'm saying, region 3 contains the carbonyl stretch. So we're going to be looking at a lot of different functional groups that contain a carbonyl group. How can we use IR to differentiate them? So let's take, for example, the pentanal. So the stretch of the carbonyl of the aldehyde, it's going to occur in the range of 1690 to 1740 reciprocal centimeters. And what's special about the aldehyde is this stretch as well that accompanies this stretch. So stretch CsP2H, 2750 to 2850 reciprocal centimeters. So the ketone carbonyl, let's say for 2-pentanone, stretch carbonyl, it's going to overlap that pretty much, 1680 to 1750 reciprocal centimeters. However, if you were looking at the IR of this versus this, you'll see this stretch in the aldehyde, whereas you won't see any similar stretch in the ketone. So you have to use all these different forms of spectroscopy to really elucidate the structure and validate your claim. So those were some basically linear aldehydes and ketones. Let's look at some structures where the aldehyde or the ketone is an actual substituent instead of a parent. So we'll call this nomenclature as substituent. So the CHO group is referred to as carbaldehyde. So for example, if we have a benzene ring, this would be called benzene carbaldehyde. Or it's shortened basically to benzaldehyde. So one of the things, in your book as you're doing your reading, these common names are still prevalent in the literature. So, and as we get to aromatic chemistry, we're going to see a lot of things are named with benz in the name. So what about, say this ring, we have a cyclohexane ring with the aldehyde, so this would be cyclohexane carbaldehyde. So those are some examples of the aldehyde CHO group. So the ketone, I'm going to say COR group, is alkanoyl. So for example, if we have this compound, which is benzoic acid, and say we're going to make a substituent off there, that's a ketone. So 1, 2, we're at the 2 position. We're going to call this 2-ethanoyl benzoic acid. And so we get the ethane part from it being 2 carbons. That's where this ethane comes from. So this 2 is if the benzoic acid is at position 1, the substituent's at position 2, ethanoyl, so we see it as a substituent. So briefly looking at the physical properties. So we're really asking, how does the carbonyl group affect the physical properties of the bulk matter? So for example, if we have ethanol, and as a study strategy, I would encourage you in your notebook, anytime you draw a molecule, do your best to name it. So just by writing that down, you're reinforcing that this name is that structure. Let's go ahead and put the lone pairs in. So we can see now that by having the carbonyl, we've introduced a dipole moment. And so the carbonyl allows for hydrogen bonding, say with a polar protic solvent such as water. So if water is an H-bond donor, the ethanal is an acceptor. And we're going to draw our H-bond as just a dotted line. So we'll call that H-bond. And so that basically tells us that, if we take some ethanal, it might be slightly miscible in water due to this interaction, this attractive force. And remember that a hydrogen bond is worth approximately 21 kilojoules per mole as drawn. So again, this would be a donor, hydrogen bond donor. This would be an acceptor. So you're going to want to be very familiar with this type of, I want to say, non-covalent interaction. If you go into the biochemistry sequence, because it's very important when you're learning about proteins and peptides, these hydrogen bond interactions, and identifying them. So that we can do the same thing if we take the simplest ketone, so propanone. This is also called acetone. It's a common solvent. You can use it to really strip paint off things. It's a good solvent for that. We use it to clean glassware in the lab. So just drawing, a molecule of water, a molecule of propanone, we can see that there's opportunity for a hydrogen bond interaction as well. So we would expect that these two to be pretty miscible with one another, and they are. So just by drawing these and looking at some simple structural features, we're able to comment on the bulk matter. So in this slide, we'll look at some synthesis of aldehydes, basically looking at some oxidation reactions. So we'll put number 1 here. We can take a primary alcohol, treat it with some conditions that do an oxidation to form an aldehyde. So as I mentioned, this is a way to communicate a structure. This is a reaction arrow. These are some conditions, and then this is the functional group transformation. So these are what we'll look at are specific examples of that, but you need to be familiar with how these things look, what the conditions are, and then what an aldehyde looks like. So for example, if we start with this molecule, this is called benzyl alcohol. So that's a common name. It's a primary alcohol. So again, primary alcohol, benzyl alcohol. We're going to treat that with this set of conditions. So this molecule, dimethyl sulfoxide, oxalochloride, dichloromethane is the solvent. So then, after all of those things are mixed together, we're going to treat with triethylamine as a base. And what that's going to do is take this primary alcohol. And so, and oxidize it to an aldehyde. So if we're counting the heteroatoms in the primary alcohol, we would say this carbon is at an oxidation state of 1. Now when we go here, that carbon's now at an oxidation state of 2. And again, we're just simply counting the bonds to the heteroatom. So there's 1, here's 1, 2. So that's what we mean by this here. In square brackets, O, this oxidation. That's an increase. So say 1 to 2. If we're counting those bonds, that's what we mean by oxidation. And again, your book may present this to you slightly different. I'm just presenting it to you in terms of a bookkeeping method where you're just counting these bonds. So that's 1 bond, it's 1, 2. Now also, if you think about how you would use IR to differentiate this from this is obviously going to have a broad OH stretch around 35 to 3,000 reciprocal centimeters. In here, that's going to be gone, and you'll have a ketone, again, say 1650 to 1740. So another set of conditions to take a primary alcohol to an aldehyde, if we're using a different substrate. Say this molecule, so 7 carbons, this would be 1 heptanol. We can use a reagent called PCC, which is pyridinium chlorochromate. And our solvent for this is going to be dichloromethane. It's a pretty common solvent because it's polar, yet it's inert to the reaction conditions. And again, these conditions are going to do a 1-stage oxidation. So the primary alcohol is going to be oxidized to the aldehyde. So this is going to be heptanal. So notice for an aldehyde, you do not have to specify the position it's at because it has to be at the terminal. That's the definition of an aldehyde. So again, we've done an oxidation. We count 1 bond. Here we count 1, 2. That's what we mean by this 1, 2 here. So another synthesis of aldehydes, and actually ketones, depending on the starting material, so is the ozonolysis reaction, where we take an alkene, and we're going to treat it with ozone gas. And end up with aldehyde or ketone, and it really depends on what the starting alkene is. So let's look at a substrate, and then we'll figure out what gives what and why. So if we start with this alkene, we're going to treat with first ozone gas and dichloromethane as our solvent. Then, that's important, as our workup, we're going to use dimethyl sulfide. So this is a reductive workup. And that's important because as we learn some chemistry of carboxylic acids, we can actually have an oxidative workup that's a little bit different and gives us different products. So the first thing we want to do is analyze our alkene. And what I'm going to do here is, in red, just highlight one of those sp2 hybridized carbons. I'm going to do that one in red. You do the other one in blue just because it's different. And so what the ozone gas is going to do, and I'll draw that with a dotted green line. It's going to cleave that CC pi bond, and then basically each sp2 hybridized carbon is going to get an oxygen to become a carbonyl. So let's go ahead and see what that looks like. So let's put our colors back in. There's that carbon. Here's this carbon. And just through visual inspection, you can see here's the carbonyl, carbon, carbon, so this is a ketone. Carbonyl, carbon H, this is an aldehyde. So you might encounter some problems where you're given an alkene, these ozonolysis conditions. So if you look, you're getting, for one alkene, you're getting two products. Sometimes you can have these alkenes which are present like in a ring. So if this was tethered to here and you clipped, those carbonyls would still be linked together through that tether. So you have to watch out for how, these different sp2 hybridized carbons are connected to one another. So maybe we can do some generalizations. So I'll draw a line here. When you're looking at your alkene starting materials, so this would be called a monosubstituted alkene. So we have a pi bond, we have one substituent here, R. Now if we clip that, we're going to end up with an aldehyde plus the one carbon aldehyde formaldehyde. So this was our mono. What about a tri, or no, let's do a di-substituted. We'll say R1, H, R2, H. So we're going to clip. We end up with R1H, so we can see that's going to be an aldehyde. And then we might end up with, depending on what R1 and R2 are, if they're the same thing, you'll end up with one type of aldehyde. But if R1 and R2 are not the same, you'll end up with two different aldehydes. And again, I always encourage you to, depending on whatever these things are, try to think about what their carbon or proton NMR would look like. So in this slide, we've looked at some syntheses of aldehydes. Now we're going to look at some reduction conditions where we're actually, instead of going in this oxidation where we're going up, we're actually going to start at a higher oxidation state and then go down to synthesize aldehydes that way. So we'll call this aldehydes by reduction conditions. So let me go ahead and sort of review some reducing agents that we've seen already. So sodium borohydride, lithium aluminum hydride, and now what I want to do is introduce two more that are really based off the aluminum hydride series. And the reason that is that lithium aluminum hydride is it's a gray powder and it's typically insoluble in organic solvents. So if you think about running a reaction, you need things to be soluble so that collisions can occur and the reaction takes place. So chemists have devised derivatives of lithium aluminum hydride that do two things. They increase the solubility and they tame the reactivity quite a bit. So you remember, lithium aluminum hydride will pretty much reduce anything. So these derivatives are a little bit attenuated in a sense. So one of them is the following. So LiAlH. Now there's only one hydride, and the remaining ones have been substituted as these ethers. And so this is called lithium tritert-butoxy aluminum hydride. So lithium, there's three of them, tert-butoxy, so that's the ether portion, aluminum hydride. So this does a couple things, like I said. The tert-butyl groups are bulky, so it's a bulkier reducing agent. It has weaker reactivity than this, and it's more soluble in organic solvents. So what does this look like if we actually draw it out? So we know lithium is plus, so aluminum has to be minus. So there it is, it's a salt. So as you can see, it only donates one hydride, whereas LaH delivers 4. So you're able to control the stoichiometry a little bit better with this reagent as well. Finally, another common one that chemists use quite a bit is called Dibal, which is diisobutyl aluminum hydride. And so you'll see that this is a neutral aluminum species. So isobutyl, those are isobutyl groups. So we see diisobutyl aluminum hydride. So again, it's a 1-hydride donor. And so what are the contexts of using these reagents? So we can take an acid chloride, do a reduction to form an aldehyde. So an acid chloride is in an oxidation state of 3. An aldehyde is in an oxidation state of 2, so formally that's a reduction. So we'll look at this molecule. This is called benzoyl chloride. So again, we count 1, 2, 3. That's what we mean by oxidation state of 3. We're going to treat that with lithium tri-tert-butoxy aluminum hydride. We're going to use diethyl ether as our solvent, and we have to do then a mild acidic workup. And so just as we said here, we're getting the aldehyde. So the aldehyde is CHO. And we count 1, 2. That's where we get oxidation state 2. So we're going 3 to 2. That's the reduction, and this is called benzaldehyde. So we can also do another oxidation state 3 reduction. So we can take an ester, we can do a reduction to an aldehyde. So again, an ester is at oxidation state 3. We're doing a reduction to the aldehyde at oxidation state 2. So for example, if we have this ester, this would be called ethyl pentanoate. We're going to treat with this compound called Dibal, diisobutyl aluminum hydride. The solvent we're going to use for that is a nonpolar solvent called hexane. And then we do an aqueous water workup. So if I'm saying this is at oxidation state 3, it's going to be reduced to oxidation state 2, so it has to be an aldehyde. And here we're ending up with pentanal. So what's nice about this reagent, Dibal, is that you can do a controlled reduction from 3 to 2. And so why do we need these reagents? Again, sodium borohydride will not do this reduction. If you were to take this molecule and treat it with lithium aluminum hydride, it would go from oxidation state 3 to 2 and then 2 to 1 all in the same reaction. So you'd actually end up with the primary alcohol. So that's another reason why these different reagents exist is a word called chemoselectivity. How can we control the reduction in this sense? So in our next slide here, we're going to look at one more aldehyde synthesis / reduction. So this is basically getting a functionally equivalent group into a molecule using some chemistry that we know, and then using one of the existing reducing agents. So let's just dive into it here. If we have this alkyl halide, which is a primary allylic bromide, and we treat this with potassium cyanide, so we've seen that through SN2 chemistry, and then we're going to use DMSO as the solvent. So potassium cyanide, it's a salt. It's going to do an SN2 displacement of the bromine to get in our nitrile group. So now this carbon, if you count 1, 2, 3, it's at an oxidation state of 3. So it will also be affected by Dibal. So we can treat with Dibal, diisobutyl aluminum hydride. Again, the solvent's typically hexane. Then we do an aqueous workup. This will actually afford us the aldehyde. And so what actually happens, just so we can see, is that this proceeds through an intermediate. So we have H, Al, I'm going to put isobutyl here. Essentially, the hydride is going to be delivered to that carbon. We're then reducing that oxidation state. So we have N minus now. We've added our H, and we have our Al, isobutyl. So these will actually form a bond to one another. So let's just draw that. So they'll form this complex. So they'll basically just sit there as an intermediate in the reaction until we add water. And so I'm going to just, in green, highlight this oxygen. So that oxygen will become the oxygen that's incorporated into the aldehyde. So essentially, this compound will break down because water will attack it. So notice 1, 2, and we're retaining that in the product 1, 2. So we've gone from 3 to 2. So we've done a reduction to get our aldehyde. So in wrapping up this screencast, we'll spend a little bit of time talking about the synthesis of ketones. We already saw one reaction in the oxidative cleavage of alkenes using ozonolysis. So let's look at a fresh reaction. So let's say nitrile, then Grignard to ketone. And so we'll look at a specific example of that being, say, this compound, benzonitrile. We're at an oxidation state of 3, look, 1, 2, 3. And say we want to treat that with ethyl magnesium bromide. Again, that's a Grignard reagent. This metal is positive, this carbon's negative. We're going to run the reaction in diethyl ether, and then we're going to work it up with dilute acid. So what's happening? Nitrogen's delta minus, this carbon's delta plus. This negative charge attacks here. The sp hybridized carbon then changes to sp2. So we actually sit at this intermediate So we're going to sit at this, this sort of N minus Br plus. I'm just drawing it as a bond for now. So it's going to sit here until we add this acid. So we add the dilute acid, and we end up with the ketone. So again, this oxygen here is the source of the oxygen that's incorporated into the product. So just to keep track of the oxidation state, we're now at oxidation state 2. Again, 3 to 2. So this process overall is a reduction, but anytime you take a nitrile with a Grignard, you're going to get a ketone. So one final reaction, we'll look at two different conditions. So if we take a secondary alcohol, again, I'm showing you this in different sort of ways of representing this just to keep your mind thinking about what these things mean. A secondary alcohol undergoing an oxidation will give you a ketone. So one set of conditions. So this molecule called 1-phenyl ethanol, as we saw before with DMSO, oxalochloride dichloromethane, then triethylamine. This oxidation, look, if we count, we have a secondary alcohol. The carbon bearing the alcohol, we count 1, 2, that's a secondary alcohol. We're at an oxidation state of 1, so we're going from 1 to 2, because these are both carbon. When this goes up an oxidation state, it's a carbonyl, and it ends up being a ketone. So this molecule is called, by its common name, acetophenone. So an alternative set of conditions is using the PCC reagent, pyridinium chlorochromate. Again, 2-butanol, secondary alcohol, PCC, dichloromethane, gets the ketone, 2-butanone. So really, in addition to learning these reagents, you should really be counting the oxidation state, because I think that's really helpful in managing these different conditions. So what is an oxidizing agent? What is a reducing agent? So if you understand just this simple counting procedure, you can say, okay, If you were not given this and just this and this, and you saw that that's going from 1 to 2, you can say, okay, that's an oxidation. What oxidants do I know? So PCC or these conditions. So that's a way to help manage the amount of information that we're going to be plowing through this semester. So in this screencast on aldehydes and ketones, we've seen some nomenclature, physical properties, and then the synthesis of those functional groups.